December 1944. A German field workshop somewhere behind the lines in the Ardennes. A Wehrmacht mechanic is holding two engine components on his workbench. One came from a Tiger tank sitting 50 meters away in the snow. The other came from a captured American Sherman, salvaged from a wrecked ordnance truck. He sets the American part down beside a second American part. Same model, different tank, different factory, a different corner of the United States entirely, and does something that should not, by every professional instinct his career has trained into him, be possible. He swaps them. No filing, no grinding, no 2 hours hunched over a vise with calipers and a hand file, coaxing one surface into agreement with another. The part simply fits. If you have spent your working life inside the German engineering tradition, this is not a small observation. It is a quiet, mechanical impossibility. In the shop where this mechanic trained, every apprentice absorbed the same unspoken law before he was permitted to touch anything that mattered. A part belongs to a machine, not to a class of machines, not to a model, to one specific engine, one specific transmission, matched by a skilled hand and a micrometer until it agreed perfectly with its neighbors. The Tiger sitting in the snow nearby had been assembled exactly this way. Bolt by bolt, gear pair by gear pair, each component individually mated to the machine it would live inside. Pull the transmission from that Tiger and try to drop it into the Tiger parked beside it, and a competent German mechanic would need the better part of 2 days with a file and a set of gauges before it settled into place. And here, in a plain wooden crate shipped 3,000 miles across an ocean still patrolled by hostile submarines, sat parts that fit any Sherman, any Jeep, any Garand rifle, anywhere the crate happened to be opened. German mechanics who encountered this across 1944 and 1945 reached, again and again, for the same word, the word that recurs with striking consistency in post-war Allied interrogation transcripts whenever a German officer or engineer was asked to explain American production. Unbegreiflich. Incomprehensible. What these men were looking at was not superior German engineering losing to superior American engineering. On almost every individual comparison, the Germans built the finer object. What they were actually looking at was something considerably stranger, the visible tip of a decision made roughly a century and 20 years earlier in a Virginia armory workshop and carried forward since through 2 federal arsenals, a stubborn Connecticut clockmaker, an autodidact in a converted wagon shed outside Detroit, and a Danish-American production executive drawing sketches on hotel placemats at 4 a.m. The decision itself was almost embarrassingly simple to state, and nearly as radical, in its own quiet register, as anything else the century produced. Do not make the perfect part. Make the same part. To understand why nothing in any German workshop on the continent could produce a crate like that one, the account has to go back much further than 1944, to a demonstration staged in Paris in 1778, a letter an American ambassador wrote home about it, and a century-long argument, fought almost entirely in workshops and patent offices rather than parliaments, over what a factory was actually supposed to be for. Consider the problem facing anyone trying to arm a soldier in the year 1778. You find a gunsmith, a master who has spent 2 decades learning his trade. He shapes a stock from a rough plank of walnut, filing and fitting until the wood answers his hand. He takes a barrel forged locally and files it until it seats correctly against that specific stock. He assembles a lock mechanism, springs, screws, a flint jaw, filing each individual piece until it mates precisely with its neighbor. When he finishes, he has produced one musket, balanced, elegant, every surface married to every other surface with real craft. He has also produced the only musket in the world that will ever contain those exact parts. If the lock breaks in a soldier's hands on some future battlefield, and that soldier strips a spare lock from a dead comrade's weapon, it will not fit, not quite. A shoulder here, a pin diameter there, some difference too small to see and too large to ignore. The gunsmith, or someone equally skilled, will have to be found, and the replacement filed by hand until it agrees with the gun it is entering. Every repair is a fresh act of custom craftsmanship, performed one weapon at a time. Every army in Europe made its weapons this way in the 18th century, and every army in Europe therefore shared an identical, largely unexamined logistics problem. You could not simply ship crates of spare parts to the front, because the individual pieces inside those crates were not truly parts in any general sense. They were fragments of one specific gun, useless anywhere else. Then, in 1778, in Paris, a French gunsmith named Honoré Blanc invited a small committee of scientists and army officers into his workshop for something closer to a magic trick than a technical demonstration. On a table he had laid out 50 disassembled musket locks, their individual pieces mixed together in bins with no regard for which lock they had originally come from. In front of the assembled witnesses, he reached into the bins at random and built complete, functioning locks from components that had never previously touched each other. It was, on its face, a modest piece of theater. To the men watching, it read as something closer to a small miracle, because it meant Blanc had solved the problem nobody in European manufacturing had solved before: how to make pieces of metal identical enough to each other that any one of them would function correctly, regardless of which specific lock it had started life inside. He had built, for the first time documented in European military history, genuinely interchangeable parts. By pure chance, the American ambassador to France was present that day. Thomas Jefferson understood immediately what he was watching. This was not simply a better musket, it was a categorically different kind of object, a weapon a farmer with no gunsmithing training could repair in his own barn, using a spare part drawn from an ordinary crate. Jefferson tried to persuade Blanc to relocate to America. Blanc declined. Jefferson wrote a detailed letter home to the American Secretary of War, describing exactly what he had seen. A seed had been planted, though it would take several decades and an ocean crossing before anything grew from it. In France, the idea quietly died. Blanc's methods were judged too expensive to scale, and the French guild system resisted them at every turn. Napoleon's armies marched to war with hand-fitted muskets, like every other European force of the period. In Britain, the same pattern repeated for similar reasons. In the German states, the equivalent tradition ran deeper still: the Meister system, in which a craftsman spent a decade or more mastering one specific trade before his judgment was trusted at the bench. A German workshop in 1800, in 1850, in 1900, organized its production around exactly this figure. The best worker was the one who could feel a surface by touch and judge, by eye alone, whether it truly mated with its neighbor. America in 1800 possessed almost none of this inherited tradition. No centuries-old guild structure, no deep well of master craftsmen passing techniques down through generations of apprentices. What it did possess was a brand new federal government that urgently needed muskets in quantity, and almost no skilled labor available to produce them by the traditional European method. In 1794, Congress authorized 2 federal armories, one at Springfield, Massachusetts, one at Harper's Ferry, Virginia, with a specific, if quietly stated ambition buried inside their founding charters: interchangeable parts not as a parlor demonstration, but as the standard method of manufacture itself. For roughly the first 2 decades, both armories failed at this outright, falling back on conventional hand-fitting. They kept trying anyway. The man who actually cracked the problem was John H. Hall, working at Harper's Ferry beginning in the 1820s. Hall's specific insight was that interchangeability could not be achieved through better craftsmanship at all. It required removing the craftsman's judgment from the equation entirely. Replacing it with a fixed physical reference, every single part had to match before it was permitted to proceed to the next stage of production. Hall designed a system built around 63 master gauges, precisely machined steel templates, against which every single component was checked before assembly. A part either matched its gauge or it was rejected outright and reworked or scrapped. No exceptions, no judgment calls. No skilled hand quietly correcting a marginal piece to make it acceptable. This solved the interchangeability problem, and it created an immediate commercial one. Hall's gauges took years to develop. The specialized machinery required to hold a workpiece rigidly in place while it was cut had to be designed essentially from first principles, since nothing quite like it existed yet. Early interchangeable parts rifles were not, in the 1820s, actually cheaper to produce than conventional hand-fitted weapons. Hall's achievement was a scientific and engineering breakthrough well before it became a commercially attractive one. This is precisely the point at which most nations would reasonably have stopped, and most did. France had already stopped. Britain stopped. A considerable number of American factory owners, weighing the upfront cost against uncertain returns, stopped as well. The United States, as an industrial culture rather than any single firm, did not stop. And the specific reason it kept going deserves its own account, because it runs through a Connecticut clockmaker rather than through any government armory at all. In 1806, a clockmaker in Plymouth, Connecticut, named Eli Terry, signed a contract that struck his contemporaries as close to fraudulent in its ambition. 4,000 clocks delivered within 3 years. The context makes the number's audacity clear. A single skilled clockmaker of the period produced, on average, roughly a dozen clocks annually by conventional hand methods. Terry had just promised, working essentially alone in a small, water-powered workshop, to exceed 1,300 clocks a year. Contemporaries assumed bankruptcy was the only realistic outcome. Instead, Terry harnessed his water wheel to drive a milling machine and built jigs that held wooden clock gears in fixed, identical positions while a cutting tool shaped them, removing every unnecessary decision a human hand might otherwise have needed to make. He delivered all 4,000 clocks on schedule. They were not the finest timepieces available anywhere in the world, but they were inexpensive enough that ordinary farm families, for the first time in American history, could afford a working clock on the kitchen wall. Terry had independently discovered, in a small Connecticut workshop, essentially the same underlying principle Hall was working out at Harper's Ferry around the same period. Design the product around the machinery required to produce it identically at scale, rather than designing the product first and treating manufacturing as an afterthought. And volume production of a kind no individual craftsman could ever match becomes achievable. This was the seed. Over the following century, it grew into something considerably larger. By 1850, Samuel Colt was manufacturing revolvers on this same underlying principle at his Hartford factory. Remington applied it to typewriters a generation later. Singer applied it to sewing machines by 1890. Each successive company extended Hall's original concept further. More gauges, more specialized single-purpose machinery, sharper design discipline that left progressively fewer decisions to individual worker judgment. European observers noticed and came to study it directly. A British parliamentary commission toured the Springfield Armory in 1854 and returned home visibly startled, filing a report that described what they had witnessed in language closer to astronomers documenting a newly discovered planet than industrial engineers filing a routine survey. Parts produced on one machine mated seamlessly with parts produced on an entirely separate machine, with no hand-fitting whatsoever required at any stage. Britain attempted to import the method, building several factories organized along the same principles the Americans used. The underlying mentality never fully transferred. The machines could be purchased and installed. The surrounding cultural assumption that a factory's fundamental purpose was producing identical objects rather than well-made individual ones could not simply be imported alongside the equipment, because British manufacturing culture remained too deeply invested in craft pride and guild-derived skill hierarchies to fully absorb a philosophy that treated individual worker judgment as, at best, a necessary evil to be engineered out wherever possible. In 1913, in a converted wagon shed in Highland Park, Michigan, a middle-aged man with no formal engineering credential pushed the entire underlying system one further decisive step forward. Henry Ford's Model T contained more than 10,000 individual parts, every one of them required to meet a precise tolerance, and every one required to be genuinely interchangeable with its equivalent on any other Model T ever produced. Ford's obsession with this principle bordered on the doctrinal. He reportedly walked his own factory floor, specifically looking for workers using hand files to adjust a part into fitting, and treated the very presence of a file on his production line as direct evidence that something further upstream had already failed. In Ford's specific formulation, a file was what a system reached for once it had already broken down. A properly engineered part required no such correction, and if a given part did not fit as manufactured, the correct response was fixing the machine that had produced it rather than filing the individual piece into grudging submission. This obsession produced, in 1913, the first moving assembly line in industrial history, a chassis advancing continuously past stationary workers, each adding one or two specific components pulled directly from supply bins with no adjustment, no fitting, no individual judgment required at any station along the line. A completed Model T rolled off Ford's line roughly every 93 minutes, against the 12.5 hours the identical vehicle had required to assemble by more conventional methods only a few years earlier. Ford had, in effect, industrialized the American system itself to a scale no one had previously attempted. Hall had produced perhaps 100 interchangeable rifles a year at Harper's Ferry in the 1820s. Ford, by the early 1920s, was producing close to 2 million automobiles annually, each containing roughly 10,000 fully interchangeable parts. Billions of individually manufactured components every single year, machined closely enough to identical specifications that any worker could reach blindly into any bin and install whatever came to hand without a second thought. Engineers from every serious industrial nation on Earth, including Japan and Germany, toured Ford's operations specifically to study and replicate it. By 1940, American trade schools, engineering programs at institutions like MIT, and the trade journals read across the entire domestic manufacturing sector had absorbed this specific philosophy into the basic professional instincts of an entire generation of engineers and machinists. The assumption that a properly designed part simply fit without adjustment, and that a crate arriving from a factory 2,000 miles distant would obviously contain parts matching your own machinery. Germany possessed a specific technical vocabulary for the underlying concept, Austauschbau, interchangeable component manufacture, and German engineering journals discussed it seriously across decades. German industry applied the principle successfully within certain high-volume product categories, small arms ammunition prominent among them. What German industry never did was restructure its entire economy around the principle as the default assumption governing manufacturing generally. The Meister tradition remained the organizing center of German production, quality as the direct expression of a skilled individual's judgment rather than, as the American approach implicitly held, the deliberate and systematic absence of any judgment a machine could be engineered to remove. This is worth stating plainly rather than treating as an obvious inferiority, because in a great many respects the German tradition produced superior individual objects. A 1938 Mercedes-Benz engine remains, by most qualified assessments, a more beautiful piece of engineering than its 1938 Ford equivalent. A Leica camera from the same period ranks among the finest precision instruments manufactured anywhere in the 20th century. German craftsmen genuinely knew how to build extraordinary things. They built them one at a time, with a file close at hand, and when the specific question the coming war would ask was no longer, how beautiful is this object, but how many of these objects can be produced, and how quickly can any one of them be repaired 3,000 miles from the factory that made it, the answer was never going to come from craft. It could only come from a system. Consider what this distinction meant concretely for a soldier in the field. An American infantryman carrying an M1 Garand in Italy, whose firing pin snapped, reached into his own supply pouch, withdrew a replacement machined in a factory in Massachusetts, and had it installed within 30 seconds. Because every M1 Garand manufactured anywhere was, for practical purposes, the same M1 Garand, and firing pins sat ready in every supply depot along the entire theater. A German soldier carrying a Carabiner 98K in the same circumstance was often reasonably fortunate, since the Car 98K had remained in production long enough for a meaningful share of its components to have achieved genuine standardization. His officer's sidearm, his unit's MG42, its optical sights, his division's tank transmissions, these told a considerably less forgiving story, one that typically ended with some variation of take it to a workshop and find the man with the file. The real test of whether the American system could scale to the specific demands of a global war very nearly did not survive its first year, and the man who saved it spent one sleepless night in a San Diego hotel room sketching a solution onto the hotel's own breakfast placemats. In January 1941, with the United States still formally at peace, Ford Motor Company Vice President Charles Sorensen, 60 years old, Danish-born, and widely regarded within American industry as its finest working production engineer, the man who had actually built Ford's 1913 assembly line, even as Henry Ford collected most of the enduring public credit for it, toured the Consolidated Aircraft plant in San Diego at the government's request, tasked with assessing whether Ford could meaningfully accelerate production of the B-24 Liberator heavy bomber. What Sorensen found appalled him. Aircraft were being assembled outdoors under the San Diego sun, precision machined components laid out on tarmac where solar heat measurably distorted their dimensions before assembly. Jigs that should have remained permanently fixed to a factory floor were repositioned as convenience dictated. Workers hand-fitted components individually, meaning every completed aircraft differed, in small but real ways, from every other aircraft nominally built to the identical specification. This was American aircraft manufacturing as it actually existed in early 1941. Sorensen did not sleep that night. Working at his hotel, the Coronado, he sketched across a stack of restaurant placemats a proposal for a single vast L-shaped factory, potentially the largest industrial building on Earth, inside which the B-24 would be assembled on a moving line following essentially the same underlying logic as the 1913 Model T, except that a Liberator bomber contained some 450,000 individual parts, roughly 360,000 rivets, and a wingspan exceeding 110 feet. By 4 in the morning, he had the basic architecture worked out. The aircraft broken into 11 major assemblies, those subdivided further into 69 distinct subassemblies, each built in its own dedicated cell with its own specialized tooling and its own set of gauges, all converging finally onto a single main line. At full theoretical capacity, Sorensen calculated the plant could complete one finished bomber every 63 minutes. Every established aircraft manufacturing executive who heard the plan considered it close to delusional. Dutch Kindleberger, president of North American Aviation, offered an assessment that became widely quoted at the time. You could not reasonably expect a blacksmith to build a watch overnight. The specific idea that an automobile manufacturer could mass-produce the largest, most mechanically complex flying machine yet built, at a sustained rate approaching 1 per hour, read to established industry experts as precisely the kind of overconfident fantasy an automobile executive with no aviation background would naturally propose. Ford built the factory regardless. It was named Willow Run, sited on a creek on land Henry Ford already owned west of Detroit. Designed by architect Albert Kahn, himself a German immigrant who had spent his American career designing large industrial facilities for Ford and numerous other manufacturers, and completed in under a year, 3.5 million square feet of production floor, a single-mile-long assembly line bent at an unusual 90-degree angle specifically because keeping the entire structure within one county's tax jurisdiction required the turn. The plant's early performance came close to vindicating every skeptic who had doubted it. The first Liberator rolled off the Willow Run line on October 1, 1942. By year's end, the plant had produced only 56 aircraft, a trickle newspapers took to mocking under the nickname "Will it run?" Congressional critics demanded formal hearings. Sorensen's promised production rate became a national punchline. Henry Ford himself, by this point in his late 70s and no longer reliably engaged in daily oversight, largely withdrew from active supervision. His son Edsel, running the project's daily operations, was already dying of stomach cancer and would not survive to see it succeed, passing away in May 1943. For several genuinely uncertain months in the winter and spring of 1943, it appeared entirely plausible that the American manufacturing system, whatever its historical successes with automobiles and rifles, simply could not scale to something as mechanically demanding as a heavy bomber. That the blacksmith and watch comparison had been essentially correct after all. What ultimately saved the project was not a change in strategy, but a deepening commitment to the same underlying principle that had built Harper's Ferry's original gauge system more than a century earlier. Sorensen's engineering team spent the first half of 1943 measuring every single part coming off every machine in the plant with unforgiving consistency. When a part failed to meet its specified tolerance, the response was never to adjust the individual part by hand. It was to locate and correct whatever upstream machine or fixture had produced the deviation, then re-verify the correction against the gauge before resuming production. Every subassembly cell was retuned repeatedly against this standard. Workers were systematically retrained until the discipline became reflexive rather than merely instructed. By summer 1943, monthly output began climbing sharply. October's total exceeded 150 completed bombers. By the following April, Willow Run produced 453 Liberators in a single month, a documented rate of one finished B-24 approximately every 63 minutes, precisely matching Sorensen's original, widely ridiculed calculation from that sleepless night 18 months earlier. By the war's end, Willow Run alone had produced 8,685 B-24 Liberators, more of a single bomber model from one factory than the entire German aviation industry had managed to produce across any comparable single type, with every individual part genuinely interchangeable across the plant's full production run. A rudder assembled in August 1944 fit a fuselage completed in October 1942 without adjustment, and a carburetor built at Willow Run slotted directly into aircraft assembled at Consolidated's original San Diego plant, at Douglas's Tulsa facility, or at North American's Dallas line, because the engineering drawings matched precisely, the gauges were identical across every site, and the tolerances were shared without local variation. At almost exactly the same historical moment, in a Henschel factory at Kassel, Germany's Tiger tank was being assembled, individually, by most direct technical measures, a more formidable weapon than anything American industry had yet produced. In a straight one-on-one engagement, the Tiger generally defeated a Sherman outright. Thicker armor, a more powerful main gun, superior optics that German tank crews genuinely valued and trusted. Each Tiger required roughly 14 days to complete, assembled across 9 sequential stages by workers fitting components largely by hand, each individual hull to some meaningful degree, its own distinct object rather than an identical twin of the vehicle assembled the previous week. When a design variant was introduced, the revised commander's cupola fitted beginning in 1943, for instance, the corresponding opening in the turret roof had to be individually cut to match that specific cupola pattern. Older and newer cupola designs were simply not interchangeable, and a field conversion between the two types meant reconstructing a meaningful portion of the turret rather than performing a straightforward parts swap. Set the two production pictures directly beside each other. American industry in 1944 was completing a 4-engine heavy bomber containing hundreds of thousands of individual parts at a rate approaching 1 aircraft per hour, with every component interchangeable across every unit ever produced, regardless of which of 4 separate factories had actually built it. German industry in the same year was completing 1 heavy tank roughly every 14 days at a single facility, with components that varied, to a meaningful and often unpredictable degree, even between machines produced in the same factory only months apart. The situation compounded further once production of the Panther medium tank is added to the comparison. Built simultaneously by Henschel, by MAN, by Daimler-Benz, and by at least 2 additional manufacturers, each operating with its own shop practices, its own preferred internal variations, and its own locally introduced modifications, not always fully coordinated with the other producing plants. A road wheel manufactured for a Panther built at MAN in a given month might fit a Panther assembled by Daimler-Benz that same month. It might equally well not. German armor historian Walter Spielberger's detailed production studies document mid-run modifications introduced at individual factories that were not always synchronized across the other manufacturers building the identical nominal design. None of this reflected any deficiency in German engineering talent. It reflected a manufacturing culture built, generation after generation, around the Meister. And when total war demanded that culture scale to unprecedented volume, it simply could not, because a culture is not a directive an official memorandum can rewrite overnight. It is something absorbed collectively over decades, and German industrial culture had absorbed, across those decades, the specific conviction that genuine quality originates in a skilled individual's trained judgment, rather than in a system deliberately engineered to make that individual judgment unnecessary. When American industry needed additional aircraft, it built additional factories and installed additional gauges. When German industry needed additional tanks, it searched for additional master craftsmen. There were never enough of them to find. All of this remained, at the level described so far, a story about factories. The place where the difference between these two manufacturing philosophies became a specific matter of life and death was not inside any factory at all. It was on the actual battlefield, in the exact moment a tank broke down and its crew discovered what happened next. On any ordinary morning during the war's final year, at a forward American ordnance depot somewhere in France, Belgium, or the Netherlands, wooden crates were being opened continuously. Replacement transmissions, final drives, track bogies, complete engines, radios, machine guns, even typewriters and medical instruments. Each part stamped with a specific part number, each manufactured to one shared engineering drawing, each genuinely interchangeable with any other component bearing the identical number, regardless of which of several factories, on either coast, had actually produced it. Consider a Sherman limping into such a depot with a failed final drive. American engineers had deliberately mounted the Sherman's final drive at the front of the hull, specifically because they had anticipated, correctly, that this component would fail reasonably often under combat stress and would need rapid field replacement. A three-man team could complete the swap in 5 or 6 hours. The tank returned to active operations, and the failed unit went to the rear for potential rebuilding, re-entering the supply chain if salvageable, or being scrapped outright if not. A Panther suffering the identical failure, and Panthers failed at their final drives at a broadly comparable rate, a known weakness stemming from a drive assembly originally engineered for a 30-ton vehicle, now supporting one that had grown to roughly 45 tons, confronted a fundamentally different physical problem. The Panther's final drive sat inside the front of the hull, rather than externally accessible. Reaching it required partially disassembling the vehicle's front structure entirely, converting what should have been a routine field repair into genuine workshop-level reconstruction. Compounding this specific design disadvantage, spare parts availability for the Panther had deteriorated sharply by late 1944. German production records document the percentage of total tank industry output allocated to spare parts falling from roughly 25 to 30% in 1943 to approximately 8% by late 1944, meaning that where 4 completed tanks in 1943 had generated spare parts output roughly equivalent to a fifth vehicle, by late 1944, that same equivalent spare parts output required 12 completed tanks to generate. The underlying policy driving this collapse rewarded German factory managers specifically for completed new vehicle output rather than for total fleet readiness, creating a direct institutional incentive to push finished tanks out the factory door while treating spare parts production as an afterthought, competing for the same finite raw materials and skilled labor. The practical consequence, by 1944, was that several German panzer divisions maintained more disabled tanks than operational ones at any given time, and German maintenance units responded by cannibalizing, a term that recurs constantly throughout surviving 1944 and 1945 German maintenance records, describing the systematic stripping of parts from vehicles judged unrepairable to keep other vehicles running. One surviving unit record from Panzer Regiment 26's 1st Battalion, dated March 1944, documents the deliberate destruction of 2 Panthers, numbered 132 and 332, that had not actually been struck by enemy fire at all. Both had already been cannibalized down to the point of uselessness, their remaining functional parts already redistributed into other vehicles, and were then destroyed outright specifically to prevent their capture by advancing Soviet forces. An American ordnance mechanic performing the equivalent Sherman repair in the same period had, by contrast, essentially never needed to cannibalize another vehicle for a working transmission. He filed a requisition slip specifying a part number and a crate containing exactly that part, manufactured to exactly that specification, was handed to him. It fit. This was not the exceptional case. It was simply how the system was built to function. Documented post-war interrogations describe a specific, recurring moment among German mechanics who encountered captured American ordnance stocks during the Ardennes offensive. Not admiration for any individual American weapon, but a quieter, more unsettled recognition triggered specifically by the spare parts themselves. Components cross-referenced by identical part numbers across factories on opposite American coasts, every single one of them genuinely, verifiably the same piece, regardless of its point of origin. Germany was not, in any meaningful sense, entirely unaware of interchangeable manufacturing as a concept. German engineering literature had discussed Austauschbau seriously since the late 19th century, and German industry had implemented the principle successfully within specific high-volume categories, small arms ammunition foremost among them. What German industry had never done was restructure its entire economy around the principle as a governing default. The clearest surviving evidence that German planners eventually grasped the full scale of what this omission had cost them is not any single interrogation quotation. It is a tank that was never actually built, the Panther II. Proposed in February 1943, the Panther II's surviving design documentation makes for quietly striking reading. It states, in almost apologetic bureaucratic language, that the new design was intended to share components directly with the Tiger II, genuine interchangeable parts between two entirely separate tank models within the same national arsenal, justified explicitly in terms of production efficiency and simplified field logistics. Pause on the specific historical irony embedded in that document. In 1943, German engineers, writing and thinking entirely within the Meister tradition's own professional vocabulary, were formally proposing as a forward-looking design goal something American industry had already treated as an unremarkable manufacturing baseline since the 1820s, and reaching, moreover, only for interchangeability between two related models, a considerably more modest ambition than the full cross-factory, cross-model standardization the American system had achieved as a matter of course decades earlier. The Panther II project was canceled after a single prototype. Germany's wartime industrial base by 1943 no longer possessed either the surplus capacity or the remaining time to execute a genuine restructuring of this scale. Germany had entered the war already committed to a manufacturing philosophy that could not scale past a certain point under sustained pressure, and by 1943, its own engineers understood this clearly enough to write the acknowledgement directly into an official design proposal. The final production tallies make the practical consequence unambiguous. By the war's end, American factories had produced roughly 49,000 Sherman tanks against a combined German heavy and medium tank output of approximately 8,000 vehicles across all types, 1,347 Tigers, 492 Tiger IIs, and roughly 6,000 Panthers. The raw production ratio runs close to 6-to-1 in America's favor. The more operationally decisive ratio, though, never appears in simple manufacturing tallies at all. It is the ratio of vehicles actually available for combat on any given day. Through late 1944, a typical American armored division maintained somewhere between 70 and 90% of its tanks in operational condition at any time. German panzer divisions in the identical period frequently operated below 50% readiness, in several documented cases dropping under 30%, the remainder sitting immobilized in workshops or simply waiting, often permanently, for parts that were never going to arrive. American ordnance battalions reinforced this readiness advantage with dedicated recovery vehicles built specifically to retrieve damaged Shermans directly from the battlefield rather than waiting for a lull in combat. A logistics investment German maintenance units, chronically short of both vehicles and fuel by 1944, could rarely match. Extend the resulting gap across 2 full years of sustained campaigning, and the effect compounds dramatically. American industry was not merely outproducing German industry in raw units. It was keeping a substantially larger share of its existing fleet actively in the fight at any given moment, while German industry built individually superior machines that then sat disabled, their crews reduced to functioning as improvised infantry, while waiting for repairs that a fundamentally different manufacturing philosophy, elsewhere, had already solved as a routine logistics problem decades earlier. American economic intelligence teams, staffed by figures including George Ball, Paul Nitze, John Kenneth Galbraith, and Nicholas Kaldor, interrogated senior German industrialists and procurement officers in May and June of 1945 and found a striking consistency. None of them blamed Allied bombing alone. They pointed to something structural, the specific capacity to scale that German industry had never built. Albert Speer, Germany's wartime armaments minister, was the most candid of them. acknowledging that German industry had never been fully mobilized, had never internalized a genuine mass production mentality, and that this had cost Germany the war. An admission shaped in part by Speer's own approaching trial at Nuremberg, but corroborated independently by the surviving factory archives at Henschel, MAN, and Krupp, by the readiness ratios recorded across every theater, and by the plain fact that when American and German wartime equipment stand side by side in a museum today, the American equipment looks cruder and cheaper. It generally is. It was also the equipment that won. Return finally to the scene this account opened with. A German mechanic somewhere in the Ardennes in December 1944, holding an engine component salvaged from an American Sherman. His name does not survive in any record accessible today, and neither do his exact words in that moment. But the broad outline of what he was actually experiencing is documented with real consistency, because hundreds of German mechanics in comparable situations across 1944 and 1945 left behind interrogation records and post-war accounts describing essentially the identical recognition. What each of them was looking at was never an isolated engineering miracle. It was the visible, tangible endpoint of a civilizational decision made roughly 12 decades earlier in a Harper's Ferry armory workshop to bet deliberately on the gauge rather than the trained hand of the Meister. That decision, compounded patiently across generations of American manufacturing, eventually produced inexpensive clocks, mass-market revolvers, affordable automobiles, and household refrigerators. And when a global war finally arrived to test it, the identical underlying decision produced bombers, tanks, jeeps, rifles, and, critically, an effectively unlimited stream of spare parts for every one of them, arriving continuously in wooden crates at depots across every active theater, each part genuinely fitting any correctly designated machine anywhere on the planet. Hermann Göring's pre-war dismissal of American industrial capacity, the widely repeated claim that Americans could produce nothing more consequential than refrigerators and razor blades, reflected a fundamental failure to grasp what those specific, unglamorous consumer objects actually represented. They represented a country in which roughly 10 million ordinary factory workers had absorbed, as unremarkable common sense rather than exceptional technical achievement, the underlying premise that a factory's basic purpose was producing large numbers of genuinely identical objects. The individual names behind that achievement are, for the most part, permanently lost to history, in exactly the way the German mechanic's own name is lost. The machinists at Springfield who cut the original master gauges in the 1820s, the women working the milling machines at Willow Run in 1944, who had learned their specific trade in a 12-week training course, the millions of ordinary American civilians who collectively translated an abstract manufacturing philosophy into the physical objects that ultimately decided the outcome of the war. John Hall received, at best, a historical footnote. Charles Sorensen earned a chapter in Ford Motor Company's own official corporate history. Henry Ford became a legend, whose popular reputation gets a fair number of the underlying technical details wrong. Everyone else, the overwhelming majority of the people who actually built the system, received nothing resembling public recognition at all. What they received instead was a specific, quiet, and thoroughly unglamorous form of victory, the kind that produces no monuments, names no battles, and leaves no memorial beyond a mechanic in a captured depot hundreds of miles from home, picking up a part from an anonymous wooden crate, and discovering, with no adequate word in his own professional vocabulary to describe the experience, that it simply fit. A war of this scale was never going to be decided by whichever side built the more beautiful individual weapon. It was decided by whichever side built the greater number of weapons that could actually be repaired within the time any given battle allowed. Germany built beautiful weapons. America built weapons that could be fixed. And standing behind that specific difference sat roughly 120 years of largely anonymous men and women cutting master gauges, drafting engineering specifications, running milling machines, arguing over acceptable tolerances, and insisting, one quiet technical decision at a time, that no part deserved to be called a part unless it was identical to every other part sharing its number. That argument was neither dramatic nor especially interesting to anyone outside the trade that conducted it. It was also, in the end, the argument that decided the war.